Hello, my name is Sami Myllymäki. I'm university researcher from the Microelectronics Research Unit, University of Oulu. Today my 6C talk is research on microwave composites. The future of electronics is divided into different fields of usage. And electronics are integrated with new materials and structures on different kind of fields. The first one is the wearables, where the electronics is integrated and immersed in the body of human beings, inside or outside. Second one is the travel, where the cars are changing. Are they flying on or on the fields? We don't know that yet, but the electronics are the parts of the devices. And then the home, what is the home in the future, how the electronics is integrated on the walls, floor, roof, and so on. The technology is missing. The content of my presentation are the functional composites, how they are used in microwaves and higher frequencies, how the material functionalities are related on the applications, how we can do the functional materials, and how we can measure them. What are the functional materials and how they are manufactured for the components? As a definition, functional materials have specific functions or electromagnetic properties that allow them to perform in certain application or even outperform on those applications. How we can make the materials? In the first place, we need the first materials as a matrix or binder material, and then the functional materials are the particles that are inserted in the first material, and we can change the quantity and share, even the shape and size of those particles. The third one is surfactants, for example, for the used particles, in order to avoid that they stick together or something else. And normally solvent materials are used in binder material, and then we can use also additional materials besides those. For example, adjusting the processing quality parameters of whole thing. And then the researcher duty is to circulate this many times. What is the research process for it? It is multidisciplinary research process where we start from material sciences, for example, electroceramics, nanomaterials, other composites, different kinds of polymers. Then we need the manufacturing processes that are related on the materials, for example, micro and nanomachining, and compression and injection molding are used for component manufacturing. Presently, we have applied materials for 3D, 2D printers, and many application areas are divided into additive or structural electronics applications. Applications for electronics are varied, for example, high-end wireless components, IoT devices, for example, sensors, different wearable electronics for people, printed electronics, actuators and sensors, and energy harvesting components. And all of these, we need the modeling softwares and characterization devices. And then again, engineers and researchers are going around the cycles many times to optimize the applications or whatever are the parameters we are adjusting. I have here 4 different examples of composites and devices that are used in RF applications. The first one consists dielectric polymer ceramic material where the high permittivity ceramic filler particles are inserted in synthetic polymer, this oil-based polymer, and then we can provide high-quality capacitors and wideband capacitors, and they can also be applied in antennas. If we replace the synthetic polymer to ceramic material, we can present similar dielectric all-ceramic composites where high permittivity ceramic filler is in the another ceramic material and the whole composite is fabricated in room temperatures. And then the application area is similar except the high temperature tolerance which we can achieve. Third application are the magnetic polymer ferrite composites where the high permeability ferrite particles are inserted in the synthetic polymer, and then we can provide inductors and wideband inductors. The fourth example is conductive or dielectric nanocellulose material where 2D transition metal carbide filler particles are applied in nanocellulose material. Here we have several examples of components which we are fabricated from those materials. Right up corner we can see the PMMA polymer barium titanate composite that is printed on top of rigid white ceramic substrate which is like that. And then the functional material is wideband printed on top of the structure. Right down corner we can see another application where the all ceramic composite paste lithium molybdate and barium titanate is printed top of the flexible surface where the polyimide material is used. And then I have example here how they looks like in this flexible polymer. The third device, left down corner, which is fabricated PMMA polymer barium hexaferrite. It's a black one in the middle, and there we can vary different kind of flake and sphere shape particles. And the fourth one, left up corner, Maxine nanocellulose RF absorbers are manufactured with varied cell structures by utilizing temperature gradient freeze drying technique where the honey cell structure is changed by the direction of freezing drying process. What are the main benefits for electronic devices which can achieve by the functional composites? At first, the designer can adjust the physical size of the device. Then he can change the shape or form of device. And the new one is the material properties that can be adjusted by changing the content in materials. And then we can improve the degree of freedom in microwave design. And based on these principal reasons, we can add more benefits. For example, the optimized material usage, we can save material by that. Or we can reduce weight because we don't use so much material on it. Or optimize area that is used in certain purpose of electric functions. And other benefits are also that they are normally comfortable to use or good looking. Or back to the technical benefits, we can increase the mechanical durability, flexibility, and stretchability. In certain cases, we can achieve high temperature tolerance, high quality factor, which means that we can reduce the signal losses. We can increase the integration degree, which normally comes to the benefits of frequency bandwidth. And in the end, we can improve the signal quality because we can improve the signal level and reduce the noise. So these techniques and functional materials allows us to provide new technology platform where we can have a solution for the future electronic integration, and future can be done. Thank you.